The Electrical Power Generating and Distribution System, EPGDS, is comprised of AC and DC power sources. The AC system consists of two engine-driven integrated drive AC generators, IDGs, one auxiliary power unit-driven AC generator, APU generator, one ram air turbine-driven AC generator, RAT, and one AC external power input. The DC system consists of one DC external power unit and two nickel-cadmium batteries. The EPGDS is normally operated in the automatic mode, whereby selection of the power source for each bus will be accomplished automatically. The integrated drive generators, IDGs, are mounted on each main engine's gearbox. Constant frequency AC power from the IDG is obtained by converting variable input speed from the engine gearbox through hydromechanical means, constant speed drive, CSD, into a constant generator speed. The IDG operates at a rated 40 kilovolt amp, 115 volt AC, 400 Hz 3-phase, with an input speed range of CSD 4618 to 8130 RPM and an output speed of CSD 12,000 RPM. The generator to the main engine gearbox uses a V-band mounting flange. For safety, the IDG features an input shaft shear section. The IDG and CSD operation and lubrication oil system is connected to an external air-cooled oil cooler, ACOC, to maintain proper temperature. For maintenance purposes, the IDG requires visual inspection of the oil level, a changeable oil filter, and oil. Operation of the IDGs is monitored and controlled by the generator control units, GCUs. The two IDG selector knobs are located on the electric control panel in the cockpit and must be in the auto position during normal operation. The auxiliary generator is mounted on the auxiliary power unit, APU. Constant 400 Hz frequency AC power is maintained by rotation of the generator with a constant APU engine speed. The APU generator is rated at 40 kilovolt amp, 115 volt AC, 400 Hz 3-phase, at an APU engine output speed of 12,000 RPM. For safety purposes, an input shaft shear section protects the generator. The auxiliary generator lubrication system is integrated within the APU oil system. The APU generator control button is located on the electric control panel in the cockpit and must be in the latched position during normal automatic operation. The ram air turbine system, also called the air-driven generator, is installed in a bay in the right side of the aircraft nose section. It provides emergency electrical power for the airplane in the event of a loss of all other sources of AC electrical power. In the event of an in-flight loss of AC power, the ram air turbine is deployed automatically into the airstream surrounding the aircraft. The kinetic energy of airflow across the turbine is converted into mechanical power to drive the AC generator. The 3-phase AC generator produces 15 kilovolt amp continuous electrical power at 115 to 200 volts, 400 Hz stabilized. 400 Hz stabilization is accomplished by the automatic mechanically regulated variable pitch angle of the turbine blades. The ram air turbine can also be deployed manually by a flight crew member using a deployment lever located in the console between the flight crew seats. Electrical power from an external source may be supplied to the airplane through the associated AC or DC receptacle. 3-phase stabilized 115 volts AC 400 Hz is available. AC power is activated by switching on the ground service switch on the ground service panel. The operation status is indicated by illumination of the avail or in-use lamp. AC and DC ground service buses are powered independently of the other buses. 28-volt DC external power is on after activating the DC ground service switch, and will be indicated on the MFD synoptic page. This external power is used to start the APU. In case of releasing the parking brake with an external power AC or DC connected to the airplane, the caution message GPU connected will be shown on the ICUS. 2 nickel-cadmium batteries, rated at 22.8 volt, 27 ampere hour, provide the essential loads in case of power failure of all generators. Battery 2 also provides power for APU start. Any available AC source will provide charging for both batteries. The left and right integrated control centers are located in the temperature and pressure controlled mid-E bay. Access to this equipment is through the mid-E bay floor access hatch, located on the aircraft port side behind the left wing. Both integrated control centers provide control, protection, and distribution of primary AC and DC electrical power. The ICCs are mounted and bonded using 4 bolts through the 4 mounting feet. Cooling air is provided from the Aircraft Air Management System, AMS, and drawn through the TRU to ensure adequate heat dissipation. All other ICC components are cooled by natural convection. All normal maintenance for removal and replacement of the TRUs, GCUs, EPM, contactors, relays, fuses, and circuit breakers is performed through the front of both ICCs. The internal bus bars are not accessible without removing the entire integrated control center. The contactor baseplate assembly, terminals, and wire connections are not accessible. Current transformers are located on the baseplate and are mounted behind the right ICC and left ICC AC contactor baseplate assembly. Precautions should be taken to ensure proper electric power and that electrostatically sensitive device safety considerations are practiced while performing maintenance on the ICCs. An ESD wrist strap should always be worn during removal of external power modules and generator control units, as these line replaceable modules are static sensitive modules. The Emergency Integrated Control Center, EICC, is located in the temperature and pressure controlled forward E bay. Access to this equipment is through the forward E bay floor access hatch, which is located in front of the nose gear. The EICC provides control, protection, and distribution of primary AC/DC electrical power. The EICCs are mounted and bonded using 4 bolts through the 4 mounting feet. Cooling air is provided by the air management system and drawn through the TRU to ensure adequate heat dissipation. All other EICC components are cooled through natural convection. All normal maintenance for removal and replacement of the essential TRU, contactors, relays, fuses, and circuit breakers is performed through the front of the EICC. Precautions should be taken to ensure proper power safety procedures are practiced while conducting maintenance on the EICC. The Auxiliary Integrated Control Center, AICC, is located in the temperature and pressure controlled aft E bay. Access to this equipment is through an airplane panel located in the rear of the cabin. The AICC provides control, protection, and distribution of primary AC/DC electrical power. The AICCs are mounted and bonded using 4 fasteners through the 4 mounting feet. All AICC components are cooled using natural convection. All normal maintenance for removal and replacement of the contactors, relays, fuses, and circuit breakers is performed through the front of the AICC. Precautions should be taken to ensure proper power safety procedures are practiced while conducting maintenance on the Auxiliary Integrated Control Center. Two secondary power distribution assemblies, SPDAs, are provided in the EPGDS, which interface with the Modular Avionics Units, MAU, the Integrated Control Centers, ICC, and various control display interfaces on the flight deck. These SPDAs are an integral part of the airplane utility management system to provide control and monitoring of several airplane systems. These functions are accomplished using power received from the various electrical buses and distributing it to airplane systems as dictated by logic calculations and specific airplane configurations based on factors such as flight deck switch positions. Distribution control of the SPDA is achieved through solid-state power controllers, SSPCs. These devices provide trip characteristics like those of traditional circuit breakers, but without the need for moving parts. The static inverter is located in the temperature and pressure-controlled forward E-bay. Access to the static inverter is through the forward E-bay floor access hatch, located in front of the nose gear. The static inverter is a line replaceable unit, LRU. The purpose of the unit is to convert 28-volt DC into 115-volt AC single-phase 400 Hz frequency stabilized power output. The generator control units 1 and 2, the auxiliary GCU, the external power module, and secondary power distribution assembly 1 and 2 all have built-in test capabilities, which means that they can detect and isolate, locate faults that may occur in the electrical power generation and distribution system. This built-in test capability has 3 levels of functionality: continuous built-in test, fault-initiated test, and initiated test. The central maintenance computer is a support tool for the technician, used to maintain reliability in aviation systems. The interface system section of the EPGDS is used to report faults or system status of associated member system units to the Central Maintenance Computer, CMC. The messages are presented on the ICUS display. In normal operation, the information will be stored in a non-volatile memory when a fault is detected and confirmed. Some additional information such as airplane identification, date and time of flight, and flight phase will also be stored if this information is available from the airplane communication bus. In maintenance operations, the CMC can command a member system of the airplane to perform initiated tests, to display system parameters, or upload memory contents of a member system. Abnormal operational conditions of the EPGDS will be presented as an associated crew alerting system, CAS message, to the flight crew on the ICUS display. 35 CAS messages have been implemented in the system controller logic, including the GCU1, GCU2, AGCU, EPM, SPDA1, SPDA2, and associated MAUs. 6 of the messages have been designated at a warning level, 26 of the messages at a caution level, and 3 have been designated at an advisory level. To ensure sufficient redundancy exists during dispatch per minimum equipment list rules, backup secondary controllers have appropriate logic for supporting the generation of necessary CAS messages. The controls of the electrical system are on the overhead cockpit control panel and have 2 subsystems: the electrical AC system and the electrical DC system. The IDG selector knobs allow control of the IDGs. Positioning the selector knobs in a normal auto position will allow automatic operation of the electric power generation and distribution system, EPGDS. If the selector knobs are in the off position, IDGs will be tripped offline and de-excited. An amber LED illuminates beside the associated selector knob to indicate which IDG has failed. By selecting the knob to the disk position and holding it in this position for 1 second, the IDG will be mechanically disconnected. Note, only authorized maintenance personnel on ground can reset a disconnected IDG. The ground power unit switch allows activation of the external AC power unit, AC GPU, from the flight deck. This switch controls the external power AC contactor, EPAC, part of the Left Integrated Control Center, LICC. If external AC power quality requirements are satisfied, but the GPU switch is in the unlatched position, then the GPU avail lamp will be illuminated and the EPAC de-energized open. Moving the GPU switch from an unlatched position to the latched position will allow automatic EPGDS operation for powering with external AC power. And if power source priority conditions are met, the EPAC will close. If the GPU switch is latched when external power is applied to an unpowered aircraft, cycling the GPU switch from an unlatched position to the latched position will be required for automatic EPGDS operation. Once the EPAC closes, the GPU avail lamp will extinguish, and the GPU in use lamp will illuminate. The constant speed drive enables the generator to operate at a constant speed of 12,000 RPM, regardless of the variable engine speed and generator load. The input shaft of the CSD drives the generator through a 1:2 ratio gearing and a planetary differential gear. As long as the input drive shaft is at 6,000 RPM, the generator operates at 12,000 RPM and produces 400 Hz. When the input shaft rotation speed varies, the generator frequency also varies. The IDG is able to achieve this constant generator drive speed if the input speed is between 4,618 RPM, which is the minimum idle speed, and 8,130 RPM. This varying speed deviation from 400 Hz generates, via the permanent magnet generator, associated electrical data to the Generator Control Unit, GCU. The GCU supplies an electrical signal to a servo valve inside the CSD. This servo valve then controls, through a control cylinder, the hydraulic log unit, which operates in a clockwise or counterclockwise direction. Because the hydraulic log unit is connected to another input of the planetary differential gear, the generator RPM increases or decreases less than the input shaft RPM. As a result, the generator frequency stays constant. The hydraulic log unit operates at 240 to 280 psi pressure. This oil pressure is maintained by a charge pump and charge relief valve. The charge oil is also used to cool and lubricate the generator and the other CSD components. It is not part of the engine oil circuit. The oil flow is between 7 and 12 gallons per minute. Drain oil from the generator and sump is supplied through a scavenge filter to an external oil cooler by 3 pumps, which are driven by the accessory drive gear on the planetary differential gear at a constant speed. These pumps are the generator scavenge pump, sump scavenge pump, and the inversion scavenge pump. The generator scavenge pump collects lubricating oil from the generator and returns it to the CSD scavenge system to supply the sump scavenge pump. The sump scavenge pump collects the lubricating oil that returns to the bottom of the CSD sump. These pumps press the oil through the scavenge filter, out of the IDG through the external oil cooler, and back into the IDG. The inversion scavenge pump acts as a sump pump during negative G operation to ensure continuous flow to the oil cooler and to supply the charge pump. A scavenge oil filter is provided between the scavenge pumps and the external oil cooler. This filter cleans the oil before it exits the IDG to prevent contamination of the external oil circuit. A differential pressure indicator, DPI, detects a plugged filter, which means it monitors the oil pressure before and after the scavenge oil filter. In this case, the red DPI button will extend as a visual indication. The scavenge relief valve is provided for filter bypass and external circuit when the filter or external circuit remains plugged. In this case, the bypass oil flows directly from the scavenge pump to the deaerator inlet. The oil is still circulating within the IDG. Therefore, the moving mechanism still receives adequate lubrication. However, the oil is not cooled when the IDG is in the bypass mode. The bypassing uncooled oil will cause the IDG oil temperature to increase and may cause the amber fault light in the IDG control panel switch to illuminate. The scavenge relief valve also opens during cold start conditions because of the high pressure created by high oil viscosity in the external circuit. The entering oil passes through a rotating deaerator. This device extracts air from the oil with centrifugal force. The deaerated oil exits the deaerator discharge and enters the charge pump. The overflow oil leaving the deaerator that does not feed the charge pump fills a holding tank inside the CSD housing. The holding tank is an all-attitude reservoir designed to assure a continuous supply of oil charge and lubrication oil through all flight attitudes, including negative G conditions. In case of malfunction, the IDG can be manually disconnected through a switch located on the cockpit control panel, controlling the electric-mechanical disconnect mechanism, which is part of the IDG input shaft. This mechanism consists of a solenoid-operated, spring-loaded disconnect plunger, camshaft, and reset ring. The manual disconnect should be performed if the associated cockpit, IDG disc, amber indicator light, and/or the IDG oil CAS message is displayed. These indicate low oil pressure or high oil temperature in the IDG. In case the operational oil pressure in the IDG drops below 140 plus or minus 25 psi, the charge pressure switch inside the CSD closes. The GCU interprets this as a low oil pressure condition. In case oil temperature in the IDG sump sensed by the temperature bulb reaches 335 degrees Fahrenheit, 168 Celsius, an IDG over temperature condition is interpreted by the GCU. In both cases, the GCU will send a corresponding signal over REC429 to the associated SPDA. The SPDA illuminates an amber lamp on the IDG disk switch. This lamp illuminates if the following SPDA input signals are active: IDG over temperature signal or low oil pressure signal, and IDG not already disconnected, and IDG input speed greater than 4,500 RPM, which senses that the engine is running. Illumination of the lamp indicates which IDG has failed. By selecting the switch to the disk position for more than 1 second, the disconnect mechanism inside the CSD provides a means of separating the transmission and generator shaft from the IDG input shaft. Selecting the switch to the disk position causes the solenoid pin to retract. This action releases a plunger which engages the cam on the transmission shaft. As the shaft rotates, the plunger rides along the cam, moving the shaft axially away from the input shaft. The IDG input shaft part remains engaged with the drive spline of the gearbox. A signal is also passed over REC429 to the respective GCU to trip the generator control relay and the generator line contactor. The APU AC generation system is used primarily when the airplane is on ground or as a backup source in flight. The system consists of the following main components: the generator unit, auxiliary generator; the generator control unit, auxiliary GCU; the line contactor, ALC; the current transformer, auxiliary generator, CT; the APU generator switch, and the crew alerting system. The APU auxiliary generator is a 4-pole, 3-phase, brushless type, oil-cooled constant-speed generator, and is rated at 30 to 40 kilovolts, 115 to 200 volts AC, 400 Hz. The auxiliary generator is installed on the gearbox of the auxiliary power unit. The generator unit and a seal plate are mounted to the gearbox via threaded studs with washers and nuts. 3 feeder cables and a neutral cable are attached to the main terminal block of the generator. An external connector provides AC output signals from the permanent magnet generator, PMG, stator to the generator control unit to adjust the exciter field DC voltage. For safety, the generator is protected by an input shaft shear section. The auxiliary generator control unit is a line replaceable module, LRM, and is located in the Right Integrated Control Center, RICC. The auxiliary GCU is a microprocessor-controlled assembly that provides the following generator control, protection, regulation, and built-in test functions: over voltage, under voltage; over frequency, under frequency; over current; phase sequence; differential fault; shorted internal wiring; shorted rotating diode system; inadvertent paralleling trip; open phase, and failure of the central processing unit of the GCU. If a fault occurs, the GCU will command the auxiliary line contactor to open and stop AC power supply to the aircraft AC power system. The auxiliary generator line contactor is a line replaceable module located in the Right Integrated Control Center. The ALC is normally held open by the auxiliary generator control unit. When the auxiliary GCU has determined that the auxiliary generator power is at 115 to 200 volts AC, 400 Hz, it sends a signal to close the auxiliary generator line contactor, which allows the auxiliary generator to supply AC power to AC bus 1 and AC bus 2. The two-position APU generator switch, located on the electrical control panel, controls the APU generator. In the normally latched position, the auxiliary generator operates automatically and provides power to the aircraft AC distribution system. The status lamp of the switch is off in this position. In the unlatched position, the flight crew can manually de-energize the auxiliary generator, which opens the generator control relay, GCR, and the auxiliary line contactor, ALC. This position is indicated by illumination of a striped bar. The emergency AC generation system provides emergency electrical power for the airplane in the event of a loss of all other sources of AC electrical power. The AC emergency system supplies the AC essential bus. It consists of the following main components: the ram air turbine, the integrated control center, and the associated generator control unit. In case of loss of AC electricity in flight, the ram air turbine AC power will provide the following airplane systems: the AC-driven hydraulic pump for the primary flight controls and the landing gear, the engine exciters, 1A and 2A, the operation of the essential lighting system, and the operation of the essential avionics and communication equipment. The ram air turbine, RAT, system, also called the air-driven generator, ADG, is installed in a bay in the right side of the aircraft nose section. It provides emergency electrical power for the airplane in the event of a loss of all other sources of AC electric power. In the event of an in-flight loss of electric power, the RAT is deployed automatically into the airstream surrounding the aircraft. The kinetic energy of airflow across the turbine is converted into mechanical power to drive the AC generator. The turbine assembly consists of two turbine blades connected to a mechanical governor, installed inside a hub housing assembly, which is connected to the generator shaft. The outside diameter of the turbine blades is 24 inches, 609.6 millimeters. The mechanical governor maintains the rotating speed of the turbine within 7,200 and 8,800 RPM by the automatic mechanical regulated variable pitch angle of the turbine blades. This rotation speed depends upon the airplane airspeed, altitude, and electrical load. The air-driven generator assembly is a three-phase, air-cooled brushless AC machine. It produces 15 kilovolt amp continuous electrical power at 115, 200 volts, 360 and 440 hertz. The ram air turbine deploys automatically in case of an airborne loss of AC power from both AC buses. The ram air turbine can also be deployed manually by the flight crew using a deployment lever located in the console between the flight crew seats. The distribution of emergency AC power is controlled and monitored through contactors, circuit breakers, relays, and protections, which is provided by the ram air turbine generator control unit and the emergency integrated control center. The main stator in the generator of the ram air turbine has an electrical heater installed to prevent moisture from freezing in the air gap between the stators and rotor during cold temperatures and icing conditions. This feature helps assure smooth startup at deployment. The ram air turbine will remain deployed and operational during the entire flight and the landing phase. After a ram air turbine system inspection procedure, maintenance technicians can restow the ram air turbine with the restow pump. The static inverter is located in the temperature and pressure-controlled forward E-bay. The static inverter can be accessed through the forward E-bay floor access hatch located in front of the nose gear. The static inverter is a line-replaceable unit. The purpose of the unit is to convert 28-volt DC into AC in order to provide the standby AC bus with single-phase 115 volts RMS, 400 Hz AC stabilized power output. The capability to convert DC into AC is 250 volt amps of electrical power. During operation, the static inverter is powered by DC Essential Bus 1. In case power is not available, to the AC Essential Bus. Then, the standby contactor inside the EICC will be de-energized, connecting and supplying the AC output of the inverter to the standby AC bus. Operation of the inverter is controlled by Secondary Power Distribution Assembly 1. This unit controls the on-off logic of the static inverter, based upon the inverter internal fault monitor and the number of AC sources available during in-flight operation. SPDA1 will set the inverter to the off status during normal operation of the Electrical Power Generation and Distribution System, EPGDS. The SPDA1 will set the inverter to the on status in case only one main AC source is available, IDG1 or IDG2 or the APU generator. If the internal fault monitor of the inverter detects a problem, a discrete status signal would inform the SPDA1 to shut down the inverter. DC power is generated by 3 transformer rectifier units, 2 accumulator batteries, or an external DC power connection. For operation of DC-powered airplane equipment, the conversion from AC power to DC power is provided by 3 transformer rectifier units. Batteries 1 and 2 are used to back up all DC buses to ensure continuous supply for DC loads. Battery 2 also provides energy necessary for an APU start. DC external power is provided by a ground power unit, GPU, and is only used to perform an APU start. The DC system of the airplane operates on 28-volt DC stabilized. There are 3 transformer rectifier units as main DC power sources. The TRUs are located inside the associated integrated control centers. There are also 2 nickel-cadmium batteries and 1 external DC power plug. DC power is generated by conversion of AC to DC by the TRUs to supply the associated DC bus. The input of each TRU is 115-volt AC, 400 Hz frequency stabilized, and the output is 28-volt DC regulated up to 300 amps of current. Both nickel-cadmium batteries have 19 accumulator cells. Battery 1 is located in the forward E-bay, and Battery 2 is located in the aft E-bay. In normal operation, any available power source will provide charging current for batteries 1 and 2, except for the DC external power. Both batteries are in operation to back up all DC buses, ensuring a break-free environment for DC loads. Battery 2 also provides electrical power for an APU start through the APU start bus when the electrical system is automatically isolated from Battery 2. The only function of the DC external power is to supply DC power to the APU start bus for an APU start. External DC power is controlled by dedicated system relay logic. Two nickel-cadmium NiCad accumulator batteries are provided for powering essential loads if transformer rectifier unit power is not available. Batteries 1 and 2 are used to back up all DC buses. To ensure a break-free environment for DC loads. Each battery consists of a steel case containing 19 semi-open NiCad cells. The cells are connected to each other in series by copper bus bars. The nominal battery voltage is 22.8 volts DC, with a capacity of 27 amp hours, at a 1-hour discharge rate. Adequate battery ventilation is provided through a tube interconnecting the battery venting nozzle to the fuselage surface. A caliper orifice close to the fuselage and a check valve on the battery vent inlet assure that gases emitted by the batteries under normal or abnormal conditions will not accumulate in hazardous quantities. Battery 1 is located in the forward E-bay directly below the SPDA-1 unit. It provides stored energy to selected equipment during normal operations and during flight in the absence of all other airplane electrical power. Battery 2 is located in the aft E-bay. It also provides the power used for an APU start through the APU start bus during ground or flight operations, when the electrical system is automatically isolated from Battery 2. Each battery is fitted with 2 temperature sensors, which are continuously monitored by the modular avionics units. Both sensors are used to provide continuous indication of battery temperature to the multifunction display and to display an ICUS warning message, battery overtemp, in red if battery limits are exceeded. The higher of the 2 temperature values sensed is the one utilized for indication and alarm. Whenever a battery over temperature condition is sensed, the pilot should isolate the battery from the charging source. Battery over temperature will never generate sufficient heat to damage the battery's surroundings, including those caused by a short circuit at its terminals or to any of its cells. Any mechanical deformation of the battery will be contained within its steel case. Maintenance requirements for the battery include a regular check every 600 flight hours and a general overhaul every 12 months. The battery must be removed from the airplane for both the regular check and the general overhaul. The regular check consists of the following: exterior cleaning, voltage check, nut tightness check, discharge and shorting of all cells, insulation check, recharge, adjustment of electrolyte level, capacity check, and cleaning of battery vents. The general overhaul consists of the following: voltage check, nut tightness check, discharge assembly and shorting of all cells, thorough cleaning and inspection of all components, check of the thermal sensors, replacement of faulty components, assembly of all battery components, insulation check, recharge and adjust the electrolyte level of all cells, capacity check of battery, and cleaning of battery vents. The airplane gets its external AC power from the ground power unit, GPU. The 3-phase 115-volt 400 Hz external AC power is used for ground maintenance and flight preparation. External DC can be used for APU start. External 3-phase 115-volt AC 400 Hz may be connected to the aircraft via a receptacle on the left-hand side of the fuselage. The external AC is used to power the AC ground service bus and the DC ground service bus without powering any other buses on the airplane. The operation of the system is controlled by the external power module, EPM. Electrical power from an external source may be supplied to the airplane through an external power DC contactor, EPDC, receptacle, located on the left-hand side of the fuselage. It allows 28-volt DC to be supplied to the APU start bus for APU start. The external DC power is used to power the APU start bus. The external DC power is operated by a system relay logic, which is part of the Auxiliary Integrated Control Center, AICC. The plugged-in 3-pin external power plug activates the voltage sensor relay unit in order to monitor the quality of the supplied DC. The DC GPU ground service switch on the DC GPU power panel is the manual control and will indicate avail when acceptable external DC quality exists. Pressing the switch will cause an in-use indication to illuminate. A DC external power switch is located on the DC external power panel. It is a push-button latching switch. This switch provides control of the external power DC contactor, EPDC. This is controlled by a power relay logic of the external power module inside the Auxiliary Integrated Control Center. If acceptable external DC power quality exists, with the DC external power switch in the off position, the DC external power available lamp, located on the DC external power panel, will illuminate via aircraft wiring, and the external power in use lamp will be off. When the external DC power source is plugged in, power quality is acceptable, and the DC external power switch is closed, the external power DC contactor will close. With the EPDC closed, the DC external power in use lamp, located on the DC external power panel, will illuminate via aircraft wiring, and the avail lamp will be off. With the DC external power switch in the off position, the EPDC will open. The cockpit control panel's ground power unit, GPU, switch provides control of the external AC power. Once the GPU is connected and power quality requirements are satisfied, a GPU avail indication will illuminate on the depressed GPU switch. Pressing the GPU switch will allow automatic EPGDS operation with external AC power, and a GPU in-use indication will illuminate. A momentary action-type ground service switch is located on the AC external power panel. It is marked as an AC GPU and includes the avail and in-use indicator lights. This ground service switch provides control of the ground service transfer contactor, GSTC, through the external power module, EPM, inside the left integrated control center, LICC. The GPU avail lamps on the cockpit control panel and on the external power panel will illuminate if power quality is acceptable, and the interlock system, pin EF, on the external power plug, is in order. When the external AC power unit is plugged in, power quality is acceptable, AC bus 1 is unpowered, and the momentary ground service switch is toggled, the ground service transfer contactor will close. The GPU in-use lamps on the cockpit control panel and on the external power panel will illuminate with the ground service transfer contactor closed. This closure of the GSTC results in only the AC ground service bus and the DC ground service bus being powered. If the AC bus 1 is powered, then the ground service transfer contactor will open. If the GSTC is energized and the ground service switch is again toggled, the GSTC will move to the rest position. AC power distribution is performed by subassemblies located in the left integrated control center, right integrated control center, emergency integrated control center, and by secondary power distribution assemblies 1 and 2. AC power for the airplane is received from two main AC channels: one auxiliary channel, one external power channel, and a ram air turbine channel. Each main AC channel receives power from associated integrated drive generators 1 and 2 through a generator line contactor, GLC1 and GLC2, and distributes AC power via AC bus 1 and bus 2. The auxiliary channel receives power from the auxiliary power unit, APU, through an auxiliary line contactor and distributes AC power through a bus tie contactor, BTC1 and 2, and via AC bus 1 and 2. External AC ground power can also be supplied to the airplane through the alternating current contactor, EPAC. The ram air turbine channel receives power from the RAT generator through the ram air turbine line contactor and distributes AC power via AC essential bus. The AC power distribution supplies AC power to various airplane loads through several AC buses. The AC buses are physically and electrically segregated to be sure that the loss of one AC bus will not affect the other. The two main AC buses are the left main AC bus 1, which is located in the left integrated control center, and the right main AC bus 2, located in the right integrated control center. The main buses supply AC power to various switched airplane loads, such as the galley feeds, galley heaters, AC fuel pumps, windshield heater control units, airplane lights, AC fans, and lavatory heaters. They also supply AC power to other loads through the secondary power distribution assembly, SPDA1 or SPDA2. The AC ground service bus is supplied out of AC bus 1 or external AC source through the ground service tie contactor. The AC essential bus, located in the emergency integrated control center, is supplied through alternating current essential tie contactor. The standby AC bus is supplied out of the AC essential bus through the standby contactor. AC bus 1, or the AC ground service bus, supplies transformer rectifier unit 1. AC bus 2 supplies TRU2, and the AC essential bus supplies essential TRU. The circuit breakers are thermal-type devices with temperature compensation. When subjected to an overload current, the breakers will trip open after a predetermined time. The circuit breakers are the free-tripping, push-pull, on-off, manual actuation type. The CB auxiliary contacts are normally open, polarized with a blocking diode. The AC circuit breakers provide protection of supply lines and cabling for all loads whose power is sourced from the AC supply system of the airplane. The AC and DC circuit breakers are located in the left integrated control center, right integrated control center, and in the essential integrated control center. On the AICC, only DC circuit breakers are installed. Some fuses are also installed on the front panel of the left, right, and essential integrated control centers. Additional circuit breakers are located in the flight deck as left and right circuit breakers side panels. Caution! All power sources to the ICC need to be disconnected prior to performing maintenance on the integrated control centers, such as opening the panels or removing any line replaceable modules. The left integrated control center provides AC and DC power distribution and protection for the main airplane buses associated with the left side of the airplane. This list shows all AC circuit breakers and their ratings, installed on the front panel of the left integrated control center. The upper AC Bus 1 CB panel can be released by unscrewing the 4 captive screws and pulling the panel away from the left integrated control center. The wires are long enough to enable replacement of any of the 3 CBs or 2 fuses. The lower front access panel of the left integrated control center can be opened after releasing the 11 captive screws, allowing easy access to the circuit breakers and other components inside. Don't forget to disconnect electrical power from the left integrated control center prior to performing maintenance. The right integrated control center provides AC and DC power distribution and protection for the main airplane buses associated with the right side of the airplane. This list shows all AC circuit breakers and their ratings, installed on the front panel of the right integrated control center. Removal and replacement is done by loosening the attached hardware and the interface wire harness. The Emergency Integrated Control Center provides AC and DC power distribution and protection for the airplane essential, standby, and hot battery buses. This list shows all AC circuit breakers and their ratings, installed on the front panel of the EICC. The first list shows 7 CBs and 2 spares, associated with the AC Essential bus. The second list shows 2 CBs associated with the standby AC bus. There is 1 front panel on the Essential Integrated Control Center. Releasing 11 captive screws provides easy access to the rear of the CB installation. Reminder: take precautions to ensure proper power and electrostatic discharge safety considerations while performing maintenance on the open ICCs. Electrical power must be disconnected. An ESD wrist strap must be worn since there are static-sensitive modules installed in the ICCs. Direct current power distribution routes primary DC power to the aircraft through sub-assemblies located in the left integrated control center, right integrated control center, emergency integrated control center, and auxiliary integrated control center. The 2 main DC buses, DC Bus 1, DC Bus 2, can receive primary DC power from 2 main DC channels coming from transformer rectifier units 1 or 2. The 3 essential DC buses, DC Essential Bus 1, DC Essential Bus 2, DC Essential Bus 3, receive power from either of the main DC buses, the essential DC channel out of the essential TRU, or either of the 2 battery channels. Both main DC buses and the 3 essential DC buses supply power to batteries 1 and 2 via the battery buses. These buses also supply the AC inverter. The left main DC bus supplies power to the DC ground service bus, DC ground service. All 4 integrated control centers have circuit breakers that provide DC power control and protection to a selection of aircraft electrical loads. The 2 SPDAs are an integral part of the electric power generation and distribution system. The SPDAs provide control and monitoring of the primary DC distribution and of DC secondary loads. Other DC system control is accessible using manual switches on the electric system cockpit control panel. The two main DC buses, 3 essential DC buses, and 1 ground service bus distribute power to various aircraft electrical loads, either through DC circuit breakers or through secondary power distribution assemblies 1 or 2. Primary DC power is distributed by line replaceable units, located in the following main components: left integrated control center, right integrated control center, essential integrated control center, and auxiliary integrated control center. Secondary DC power is distributed by LRUs located in the Secondary Power Distribution Assembly, SPDA1 and SPDA2. The left integrated control center provides primary power distribution and protection for the main DC buses located on the left side of the airplane. The left DC buses are DC Bus 1 and DC Ground Service Bus. The left integrated control center performs the following functions of DC distribution: charging battery 1, uses DC Bus 1 as a power source for DC Bus 2 of the right integrated control center, and as a power source for DC Essential Bus 1 of the Essential Integrated Control Center. The right integrated control center provides primary power distribution and protection for the main DC buses located on the right side of the airplane. The right DC buses are DC Bus 2 and DC Essential Bus 2. The RICC performs the following functions of DC distribution: charging battery 2, uses DC Bus 2 as a power source for DC Bus 1 of the LICC, uses the isolated DC Essential Bus 2 as a power source for DC Essential Bus 3 of the EICC, and as a power source for Hot Battery Bus 2 of the AICC. The Emergency Integrated Control Center provides primary power distribution and protection for the DC Essential buses located on the airplane. The essential DC buses are DC Essential Bus 1, DC Essential Bus 3, and Hot Battery Bus 1. The EICC, Emergency Integrated Control Center, performs the following DC distribution function: uses DC Essential Bus 3 as a power source for DC Essential Bus 1, which supplies the AC inverter. The Auxiliary Integrated Control Center provides power distribution and protection for APU Start Bus located on the airplane. The AICC performs the following function of DC distribution: uses battery 2 and DC external power as a power source for APU Start Bus, which supplies the APU starter motor. On the multifunction display, any operational status of the electrical distribution will be presented in form of marked colored icons or colored flow tubes. In case of a malfunction in the electrical distribution system, the ICUS will display the associated message. Secondary Power Distribution Assembly, SPDA1, is located in the forward avionics bay, and SPDA2 is located in the mid avionics bay. In the DC distribution system, SPDA1 provides secondary power control and monitoring of 3 integrated control centers: left, right, and essential. And SPDA2 provides secondary power control and monitoring of all 4 ICCs. SPDA1 consists of 20 slots for modules. SPDA2 has 26 modules that are individually replaceable. Some of these modules assist in DC power distribution. An ICUS message SPDA fail indicates a total failure of any module in SPDA1 or SPDA2, or a loss of communication with the other SPDA. This indication is shown as an advisory message. These switches allow the flight crew to disconnect the DC distribution system from the automatic operation. They also allow the flight crew to activate or disconnect both batteries. During APU start sequence, the Auto mode opens Battery 2 contactor automatically. The DC circuit breakers provide protection of supply lines and cables for loads whose power is sourced from the DC supply system of the airplane. The circuit breakers are mounted on the circuit breaker panels located on the front of the left, right, essential, and auxiliary integrated control centers. Only DC circuit breakers are mounted on the AICC. The feeder wire bundles and load output wire bundles to the DC circuit breakers are separate from the wire bundles to the AC circuit breakers. The power input and power output wires and auxiliary sense contact wires are all bundled separately to avoid disturbances by induction. The left integrated control center upper panel contains 5 DC bus 1 circuit breakers and 1 spare. The lower panel contains 7 DC ground service bus circuit breakers and 19 DC bus 1 circuit breakers plus 1 spare. The list shows all DC circuit breakers and their ratings, as installed on the front panel of the LICC. The right integrated control center upper panel contains 6 DC bus 2 circuit breakers and 5 DC essential bus 2 circuit breakers, plus 1 spare circuit breaker. The lower panel contains 13 DC bus 2 circuit breakers, plus 2 spares, and 10 DC essential bus 2 circuit breakers. The list shows all DC circuit breakers and their ratings installed on the front panel of the RICC. This shows the first front panel location of 15 DC Essential Bus 1 CBs, the second front panel location of 3 DC Essential Bus 1 CBs, the third split front panel location of 5 DC Essential Bus 3 CBs, including 1 spare CB, and the fourth front panel location of 2 hot battery bus 1 CBs. The list shows all DC circuit breakers and their ratings installed on the front panel of the EICC. The circuit breakers mounted on the front panel of the AICC are DC only, 7 hot battery bus 2 CBs plus 4 spare CBs. This list shows all DC circuit breakers and their ratings installed on the front panel of the AICC. Caution! All power sources to the ICCs need to be disconnected prior to performing maintenance. For example, opening the panels or removing line replaceable modules. The Electrical Power Generation and Distribution System, EPGDS, communications scheme provides an interface with the Avionics Standard Communications Bus, ASCB, enabling the EPGDS to provide system information via the Modular Avionic Units, MAUs, to the Cockpit Indicating and Crew Alerting System. On the interactive EPGDS communication schematic, you can view the different components, their locations, and their functions within the electrical power generation and distribution system. Operation of the electrical system can be monitored by the flight crew on the MFD Electrical System Synoptic page, which consists of both analog and discrete data. Analog data is used to display actual values like voltage, current, and generator frequencies, while discrete data is used to indicate electrical flow paths, conditions of batteries or generators. The CAS field on the ICAS panel informs the crew in case of a system failure by generating a warning or caution message and an advisory message to indicate system status.